Hello and welcome to Lecture 6 of Chemistry for the Interdisciplinary Sciences. Today we're going to keep talking about covalent bonding and we're going to start talking about the shapes of molecules. So what is it that affects exactly this shape that the molecule makes? Let's have a glance at the learning outcomes. We're going to describe factors that affect the strength of a covalent bond. We're going to look at how you map out where the electrons come from in a molecule and draw dot cross diagrams. And then we're going to use those dot cross diagrams to find the shape of a molecule as a whole and find out about the angles around that atom too. So that's what they are there for. So let's just quickly remind ourselves about covalent bonds. A covalent bond is a shared pair of electrons. The atoms share because they do not have full shells, and by sharing they can get to that full electronic configuration. And we represent those covalent bonds with that stick in between the element symbols there. Covalent bond is therefore then an attraction of two atoms formed by sharing a pair of electrons between the nuclei. Now, what's going to affect the strength of the bond? We call this enthalpy when we're talking about what the strength of the bond is. And if you have a look at your data sheet for this course, you'll see that there's a table of bond enthalpies in there that talks to you about the relative strength of the different bonds. Now, there are two driving factors for a reaction, but one of them is enthalpy. The other one is entropy that you'll hear about later. But enthalpy is the major one. Enthalpy is talking about the strength of a bond. Now, if a covalent bond is, as we saw on the last slide, the sharing of a pair of electrons, then that would suggest that all bonds should be equally strong. If they're always just being shared by pairs of electrons, why are they not all the same? The answer is it depends how much distance those electrons have to span. So if I've got two hydrogen atoms, they're really teeny tiny, they're just going to go together, aren't they, immediately? Two of those really, really short little bonds. Whereas if I have some very, very large atoms, then those two electrons are going to have to be spread out along a much longer distance. So for covalent compounds and single bonds, the longer the bond, the more spread out the electrons are, and so the less strongly they attract those two nuclei. The weaker the bond, the longer the bond, and the shorter the bond, the stronger the bond. There. The other thing that affects the strength of a covalent bond is how many bonds are there. If it's a single bond, then that is obviously weaker than a double bond, which is weaker than a triple bond. Though if you've just watched the hybridization lecture, you might now realise that the first bond is not the same as the second bond in a double bond. And so it's not the case that a double bond is actually twice as strong as a single bond. If you're interested in that, pop back to hybridization. It is an interesting thing, but not necessary for you to know. So the two factors then that we're saying are affecting the strength of a covalent bond is length and number of electrons involved, or how many bonds there are. So let's have a look at an example. Here we've got nitrogen triiodide. Nitrogen is up there in period 2 of the periodic table in the 2p block. There it is in the 2p3 position. It's got 5 electrons in its outer shell, but it's quite a small atom. But it's attached to some iodines. Iodine is all the way down there in the 5th row, I think. Yep. It's in the P5, it's in the P55 position. 5p5 position. Its proton number is 53. It's all the way at the bottom of the group 7. Now, I don't think I've ever mentioned, actually, you see under it there's astatine, and you see how astatine has a mass number in square brackets. That's because it's radioactive, and it doesn't exist for long enough for us to really care about what the natural abundance is. There is no natural abundance of that compound. Of that element. So, nitrogen being small, but iodine being large, means that the length of the bond between the nitrogen and the iodine is very, very long. And so there is an opportunity to make a shorter, stronger bond by rearranging the atoms. In this case, at the very top, you can see I've got Ni3, so that's a nitrogen atom and 3 iodines, that's this molecule down here, changes to make a nitrogen molecule, an elemental nitrogen molecule that we've already seen is an NN triple bonded thing, and iodine. Now the problem with this is, on this side, I've only got 1 nitrogen atom, and over here I've got 2. So what we need to do is balance this equation. During a reaction, you can't make new atoms or lose atoms, except for those radiochemical ones that we were looking at, but that's not normal chemistry. So in normal chemistry, we expect the number of atoms to be the same at the start as at the end, and essentially all you're doing is taking your molecule, breaking it up into new bits, and then putting them together in a different order again. So that's always going to be the case. So if we were to balance this equation, well, we only have one nitrogen atom on the left-hand side, and we need two. So we have two nitrogen triiodide molecules then. Now, if we look at the pointer, if we look at what that physically looks like, it means that I've got two lots of molecules that are Ni3, i.e. two lots of molecules that are attached like this. So that's one, and that's our second one. Like that. That's what 2Ni3 means. It means two completely separate and unattached molecules of Ni3. Those two ends rearrange to make that dinitrogen that we've seen before. So that looks like that. And then 3I2 means three lots of iodine. So I've got three separate iodine molecules there, which are themselves described as I2, so it must be two iodines joined together. So what it should be then is that I've got the same number of atoms on the left and the right. Here I've got nitrogen, I've got two of them, iodine. I have 6 iodine atoms in total. Sorry, that doesn't look like an I. Over here, how many nitrogens? Only 2. How many iodines? Yeah, I've got 6. So this is a balanced equation. So let's have a look at this reaction and see what happens. So we've got the solid down there at the bottom. We provide just a little bit of energy. And it's an interesting one, is this. This is not a normal chemist's thing to do, really. Hit it with a stick. But we hit it with a stick to provide the energy. And it seems to make a gas. So it goes from that solid, and we make this great big cloud of purple gas. The purple gas there is the iodine itself. So that's the iodine being made. We've also got nitrogen being made, and it's being made really quickly. This is exactly the same stuff. Well, sorry, not exactly the same. This is the same concept as the stuff that goes into your airbag in your car. So there's a solid in there. It's a sodium azide salt, I think. But basically, it's nitrogen rearranging into gaseous nitrogen or gaseous nitrogen, and that's what blows up the airbag there. So literally, if you are in a crash, an explosion happens in your face that is designed to protect you, which was an interesting concept for someone to come up with. So the reason that this reaction is happening is because these Ni bonds are long and weak, and this new nitrogen molecule has very, very strong, short triple bonds. And so the formation of the new stronger bonds has driven this change. And what you can do is you can look at your data sheet and add together all the bonds on one side and all the bonds on the other, and figure out whether or not overall you've ended up with stronger bonds or weaker bonds than before. This is called enthalpy. But for today, what we care about is how do those molecules physically look? So here we've got our water molecule again. We saw this in the last lecture. And in there we've got our oxygen. It's got 6 of its own electrons around the outside and 1 from each hydrogen to make 8 in total in the middle. Now, let's have a quick look then at what that means for these molecules. Notice that the water molecule here, if I count how many pairs of electrons there are 2 bonding pairs, and then there are 2 lone pairs for a total of 4. Here, we have a total of 4, and over here we have a total of 4. So all of these have the same number of electrons, but they're going to have wildly different shapes, and that's because of the number of atoms that are put together. So what we're going to do now is have a look at how do I go through the process of figuring out what shape a molecule is going to be. So we have a quick look at the water molecules behind us, especially that one there. Oh, that's confusing. That one there. You can see that it's a little triangle shape. And that doesn't make a lot of sense if you think about the idea that you've got an oxygen there and 2 hydrogens attached to it. Why wouldn't they be as far away from each other as possible and be like a straight line? The reason for that is the lone pairs that exist. So let's map them out. A dot cross diagram is essentially doing the exact same thing that this diagram at the top is doing. It's trying to say where the electrons come from. But instead of using purple and green dots, we use dots and crosses. One for each atom, and we just alternate it along the structure. What you don't need to do is have dots, crosses, squares, triangles, stars representing each of the separate atoms. All we want to know is, do these electrons both belong to the same atom, or do they come from different atoms? So when you're doing a dot cross diagram, what you're going to do is you're going to find the bonds, and you're going to say, okay, that was one electron of each type. So a dot and a cross. I don't really need to decide whether the oxygen is a dot or crosses at this point in time, and there's no convention. It's not that oxygen's always dots and hydrogens are always crosses or anything like that. You can use either one. So that's my first step. I'm representing these electrons here being shared. Then I need to represent these electrons on there, so I'm going to pop those on as dots. I've decided that oxygen is going to be dots here. I'm going to have two lone pairs like that on there. So let's clear my screen and see that drawn properly. There we go. So we've got a dot and a cross in between the oxygen and the hydrogens, and then we got the dots up at the top. It's those extra electrons at the top that take it from that linear shape. So I've got oxygen and hydrogen here, which you think they'll be repelling as much as possible. And the extra electron density at the top is what pushes it down to this shape, this strange little triangular shape there. So if you were to try and draw a dot cross diagram for HCl, which one of these three do you think is correct? So take a second to pause and give it an answer, and then we'll go through. Okay, let's take each one in turn. So let's look at A. A is looking pretty good because we got a dot and a cross in between H and Cl, suggesting that there's a covalent bond there between them. But chlorine has the right number of electrons. It needs 8 for its octet. Hydrogen has way too many electrons. It's only supposed to have 2. So that one's ruled out by these lone pairs there. B is looking better. Hydrogen does only have 2 and chlorine has 8, but we got these electrons which do not represent the covalent bond. Should be a dot and a cross there. So that suggests that C is correct. Let's double check. Yes, we've got a dot and a cross representing a covalent bond. Do we have the right numbers of electrons around each atom? Yeah, we do. And we can go even further and say, okay, hydrogen is in group 1, so I should only have 1 dot. Chlorine is in group 7, so I should have 7 crosses. Yeah, I've got 7 crosses too. So let's now think about how we draw our own dot cross diagram and how we get to that process. Step 1 is to draw the connectivity of the atoms, and that one is the tricky bit. So you've got to figure out which atoms are connected together and how do we make them happy in terms of the bonds themselves that are there. So that's step 1. Then you've got to draw each single covalent bond as a dot and a cross. And then finally, we're going to locate the lone pair electrons. So let's start with CO2. I'm going to do this one as an example, and then there'll be some ones after for you to do. If the equation is CO2, then there's only really 2 options for us to go for. We've either got the C at the end and our 2 O's hanging out on the inside. What ChemDraw does is it automatically fills up the octet for you. Or we're going to have C in the middle and oxygens on either side. Oops. So it'll look like that. Oops. So what we then do, once we've drawn those, is we say, right, will this make any sense? So oxygen only wants to make 2 bonds, which means the middle oxygen there is absolutely fine as it goes. Sorry, I'm just messing with my green screen a bit. So that middle one is fine. That oxygen does have 2 bonds, but then the carbon needs to have 4, and that's just not going to be possible. So already this structure is ruled out, and the same is true for that one. That oxygen can't get 2 bonds and not dissatisfy the carbon, the oxygen there. Oh, we might think, oh, maybe we can draw a little triangle structure. That still doesn't work though, because we still need that carbon to have 4 bonds. So that one's out. That one just doesn't work. And hopefully you get to that point yourself. You try to draw the connectivity and see if you can make it work. How about this one? Well, my carbon needs to have 4 bonds. My oxygen needs to have 2. So that satisfies the oxygen. and that satisfies the oxygen. So that must be the structure then. So it must be C double bond O, sorry, O double bond C, O double bond O. So let's pop that into the structure. There we go. Now we need to replace each of those covalent bonds with a dot and a cross. So let's do that. In this case, we got double bonds, so we're going to have 2 pairs of each. There they are. And then we're going to look at the atoms and say, something's not right. The oxygens don't have full outer shells. So we look at the valence electrons. We look at how many electrons these these atoms should have from the periodic table. Oxygen is in group 6, so it should have 6. Carbon is in group 4, so it should have 4. Okay, so carbon should have 4 dots or 4 crosses. It does. It has 4 dots, so let's say that it's dots. Or should we say, well, whatever. It's either dots or crosses, we'll find out. Oxygen has 6 valence electrons, and it currently only has 2 dots. So, that being the case, we must have some missing lone pair electrons then. So let's find them. And essentially what's going to happen is it's going to fill our octet, so it's not going to be too tricky. Oxygen should have 6 of its own dots, so that means it's missing 4 dots at the moment. So we put those in on each oxygen like that. And there we go. We got everything down. So hopefully that makes some sense. This is our dot cross structure. It's showing where all the groups of electrons are. Let's have a look at the next one. COH2. Okay, so COH2. Now, I'm learning a lesson from the last thing. I'm learning that my carbon probably wants to be in the middle because it's got the most bonds. So, I've got an O, I've got a H, and I've got a H. Let's keep those as they are. Okay, so can we satisfy this? Yeah, carbon needs 4 bonds, and oxygen needs 2. Sorry about the green up there. So that means that we must have a double bond there. And that must be the end of that one. Okay, cool. So the structure then is C double bond O and H is on either side. We're going to replace every covalent bond with a pair of electrons. So that's what that looks like. And now I'm going to look at my atoms and see what's happy and what's not happy. Well, carbon's fine. It's got 8 electrons around it. That's good. Hydrogen's happy. It's got 2 electrons around it. And it's, again, imagine that you've got like Venn diagram circles here. Oops, sorry. Oh, I can't undo that. Okay. So imagine we've got Venn diagram circles holding all of those together. Like that. So oxygen is the only one that's not happy, isn't it? Oxygen only has 4 electrons in its outer shell. It has 6 valence electrons anyway. So it must be that there are 2 lone pairs on that oxygen again. And you'll find that that is common. Oxygen will always have 2 lone pairs. Lovely. So this is called now valence shell electron pair repulsion theory. The idea of what shape is this molecule going to be. So the answer comes from, well, you look at how many electron groups there are. And I say group because a double bond counts as one group. Double bonds are locked together in physical space. And so they can't repel each other because then they wouldn't be double bonds anymore. They wouldn't be 2 bonds holding each other together. And again, if you looked at hybridization before, you've seen how they're locked together in physical space. There's a sigma and a pi bond there. But groups of electrons basically are bonds and then lone pairs. So we find out around the carbon how many groups of electrons are there. There are 2 groups because there are 2 bonds. And so what we'd expect is that they're going to repel each other as much as possible. If I have 2 things, so let's say I've got these 2 pens, I'll just move myself over. Got these 2 things, I'm going to make them repel and I want the lids as far away as possible from each other. It's like that, isn't it? So that's a linear shape for that compound there. What would the angle be along here? So I'm looking at this angle here. Well, it's obviously 180 degrees, isn't it? It's a circle cut into 2. So it's 180 degrees. So that was the question I was about to ask you. What's the bond angle? If they're repelled as much as possible, it must be 180 degrees. And there it is. So what are the sizes of the other ones? How many groups can you have? Well, for the main group, non-metals, the most is 4. So 4 separate bonds or 3 bonds and a lone pair or whatever. So if you only have 2 groups of electrons, that's your angle is 180. If you have 3 groups of electrons, then it looks like this. Let me just go to the overhead cam. Looks like that. The angle is 120 between each one. If you have 4, it's slightly different because now there's benefit. If you think about those 3 there is absolutely no benefit. Sorry, one sec. Let's just make this a bit smaller. There is absolutely no benefit to me of having this bond move up out of the plane because now it's still getting closer to this pen over here. So these are all representing groups of electrons, either lone pairs or bonds. Going that way, I get closer to that lid. Going that way, I get closer to that lid. Going that way, I get closer to this one over here. So just being in a flat plane works perfectly well. For 4 bonds, it's slightly different because now we can make use of the 3D space. So I'm not sure if that's clearer or not, but hopefully you can vaguely see that we've got, let's just try that one more time, that there, yeah, and that going forwards there. So I don't know if that shape is clear, but what I'll do instead is let's make a molecule of methane. So I get myself a carbon, I'm going to get myself some big long bonds because that's going to help us see the shape. There we go. So I'm putting together 1 carbon and 4 hydrogens. And again, what we're going to see is the shape when they are repelled as far as possible from each other. So this time it's a 3D shape. And one more. There it is. Lovely. Great. So that's the shape. And I'll show you it from a couple of angles here. But now you can see if I move this atom that way, it gets closer to that one. There's no direction I can move this atom that moves it further away from any of the other hydrogens. And so that's the shape, and I'll show you it front on as well. Oh, wait, can I do both at the same time? No, I can't. So there it is from the front on view. That's the shape there. And from the top, that's what it looks like there. Each of these angles is about 109 degrees there. So it's bigger than the 90 that you might be imagining. So if you were imagining instead that it was like this, sort of physically flat on the space, then we only get 90 degrees out there. By moving the angle, so it's more like this, that's my carbon in the middle there. And this is where we start to use wedges and hashes here. So imagine that's flat. Imagine these 2 are flat on the page. I've got one sticking out in front of my hand and one behind my hand there. That's what these wedges and hashes represent. And that angle is slightly larger by rotating out, essentially those 2 rotating over. So it would look like, basically it would look like that, wouldn't it, at 90 degrees. By allowing them to relax, we get to our 109 degrees, slightly larger space so that they can repel. And the reason that they're repelling is because they're negative electrons. They are the same charge, so they're going to repel each other in that process. So essentially what you're looking for then is how many groups of electrons are there. If there are 2, the angle's 180. If there are 3, the angle's 120. If there are 4, the angle is 109 degrees. So let's have a look at these ones. Let's do these ones together. So we already talked about carbon. Does that carbon have any lone pairs? Nope. So where are the groups of electrons? Well, there's 1 bond there and 1 bond there. Again, we're considering both bonds part of 1 group because they are physically locked together in space and they can't repel anyway. Over here, we've got 3 groups of electrons. And over here, we've got 4 in total. Great, so let's get rid of our ink and see it properly. That's going to be the angles then that we're going to see on this molecule. And I'll just move myself so you can see that. So that's how it's going to work. The angles are going to look like that. What I want you to be able to do though is to look at any molecule and start to consider what's going on with the groups of electrons. So let's have a look at water. Water has 4 groups of electrons in total. It has the two bonding pairs of electrons, so there they are, 1 and 2. And it also has these lone pairs. Now, why do you think we're thinking of lone pairs as also being locked together in physical space? Because you would think, if we've got two electrons, why don't they just whiz off on either side of the thing themselves? Well, the answer is that they are also locked into an orbital. And the orbital is what defines where they are in space. So this is 4 groups of electrons. We expect the angle to be 109. Those of you who've done chemistry before might be aware of an additional rule that we're not examining this year. But that is that lone pair electrons, given that they are not spread out at all, repel just a little bit more. So if we imagine, we go back to our model here for a second. If we imagine this, but instead of it being a little atom like this, instead it was just electron density and a much shorter, fatter bond, then it might repel these ones a little bit more than usual. So let's take those two off. Imagine that that's the oxygen there, these are the lone pairs. It would force these two electrons just a little bit further away because there's so much electron density around this atom and it's not being spread across this whole bond. We are not examining that, but it is worth knowing that it's a thing. So the lone pairs do actually restrict the size of the bond very, very slightly in there. Okay, lovely. So that takes us back to this. Basically, you're just remembering that if there are 2, then you're cutting a circle into 2. If there are 3, you're cutting a circle into 3. And if there are 4, you're going into 3D space and using the whole space to give you a bond angle of 109 degrees. Technically, it's 109.5. I don't care. It doesn't matter. So please do just use 109. If you already know from the A-levels that water would actually be 105, then that's absolutely fine. Like, that will still be marked correct. But if you are not aware of that shrinking of the size of the angle by 2 degrees for every lone pair, then please don't worry about it. There we go. So, covalent bonding is about pairs of electrons because of orbitals there. The minimum size of a group is 2 electrons, and that's related to that orbital business. And I've mentioned down at the bottom, 2-degree reduction rule is not examinable. Okay, so let's do some more examples then. I want you to go through these yourself. So you give it a go. You're going to start by figuring out the connectivity. You're going to replace the dots and the crosses the covalent bonds with dots and crosses, and then you're going to find yourself some lone pair electrons. So please pause now and do it, and then I'm going to do it myself. Okay, so step 1, HCN. We've got carbon has the most bonds there. So with HCN, the carbon's probably going in the middle, but it doesn't matter. If you experimented, you would eventually find this yourself anyway. So there's C. I'm going to put the N on one side and the H on the other. Okay, so this is not too bad. I must have to have triple bond in between the C and the N to give N 3 bonds like it needs. Carbon needs 4, hydrogen needs 1. That's all correct. So it must be HCN like that. We're going to replace every single covalent bond, or every bond with a dot and a cross, giving us that. We're going to say, how are we doing for electrons? So hydrogen has 2 electrons, so that's fine. Carbon has 8, so that's fine. Nitrogen didn't, it only had 6, so we had to put the 2 lone pair electrons on. And again, we'd have a look at the periodic table. We'd say, oh, nitrogen's in group 5, it must have 5 valence electrons. So I must have 5 dots around the nitrogen there. Whichever way you want to do it is fine. Let's try now finding the angles. So here I've got angle A, B and C. So pause again, see if you can find the groups of electrons and give it a go. See if you can figure out what the angles are. So please pause now. Okay, so let's have a look. For A, carbon. First of all, how many electrons are around that carbon as drawn? Is it a full shell? Yeah, it's got 4 bonds, so it's got 8 electrons, that's it. How many groups of electrons are there? Well, there's a single bond, so that's 1. There's a double bond, so that's number 2. And then there's another single bond, which is group 3. There are 3 groups of electrons, so what is the angle? It's 120 degrees. Don't know why it's doing that, but there you go, 120 degrees. What about angle B then? So for angle B, again, we're looking at a carbon. Does it have a full shell as drawn? Yep. So now we're just looking at groups of electrons. There's one there, one there for 2. That's the third one, and that's the fourth one. We've got 4 groups of electrons, so the angle is 109 degrees there for B. And finally for C, now here's where we don't have a full shell as drawn. So we've got 4 electrons drawn there, 2 pairs. So we must have 2 lone pairs as well, mustn't we? So let's count. We got 1 group there with that single bond, 2 for that single bond, 3 for that lone pair, and then that lone pair makes a 4th. So the angle there is also 109 degrees, though if you've already studied chemistry, you might say 107. Either way is absolutely fine there. So hopefully that makes sense to you. Please do ask in office hours if not, to get some help. So finally, we just need to name a few shapes here. The first couple aren't too bad. So at the top there, what we've got is carbon dioxide. We've got CO2. Remember, carbon is represented with black there. So that one is a linear molecule. It's just a straight line, just like a pen. So that's going to be linear. The second one here, this is a trigonal planar molecule. So it's planar because it's flat. That's what planar means, like a plane of geometry. or a desert plane, I guess, a flat area. So it's a flat triangle, and that's what makes it a trigonal planar compound there. So that's the shape there. The next one is tetrahedral. Now, if you are a complete utter nerd like me, which I really hope you are, because that's the most fun ever, you might have a load of D&D dice, or a character. So here, what I'm looking for is a D4. Here we go. So this is a D4 dice. I'll show it in both angles there. It's a little triangle-based pyramid, essentially. This is a tetrahedron. So a tetrahedron is where you've got four sides that are exactly identical, whereas if you had 6 sides, that would be a cube that were exactly identical. And that's the name of that shape, a tetrahedron. So a trigonal pyramid, essentially. There. Now, it is a trigonal pyramid, that's correct. The difference between a trigonal pyramid and a tetrahedron is sort of the difference between a cuboid and a cube. So a cuboid can have rectangular faces. A cube has to be square faces. The same's true for this. A tetrahedron has to have equilateral triangle faces, whereas a trigonal pyramid has to have a trigonal bottom, and then it can have triangles of any shape for the sides if you want. So this one is a tetrahedron. Let's just find that tetrahedron. Basically, you take every hydrogen atom and you connect them together, and that leads you to this sort of pyramid. There is one more line that you can't quite see there because of the structure. And so there you go. There's your trigonal pyramid there where all the sides are the same size. That's a tetrahedron. So those are our three basic shapes: linear, trigonal planar, or tetrahedral. The problem is that sometimes this group is not an atom, it's a lone pair of electrons. And in that case, it changes the name of the shape. So while that's a tetrahedron and all of the angles are 109, if we took off one of these atoms, so if that one wasn't there anymore, what shape would we have then? Let's have a quick think about that. What shape would that be? So it's still going to be that trigonal-based pyramid, isn't it? And this time, the sides, the triangles going up the sides of the pyramid, are not the same size as the base is. The base is bigger. And so this one is a trigonal pyramid. A pyramid with a trigonal foot. If you said triangle-based pyramid, that would be absolutely fine as well. So there we go. 4 groups, 3 of them are bonding groups, or 3 bonds in there. And we got one lone pair, which leads us to a trigonal pyramid. So I want you to know these shapes enough to look at any example and go, oh, okay, that's a trigonal pyramid, or that's a tetrahedron, whatever it is. Finally, we could get rid of one more of these atoms and just have another lone pair, as in water. When you do that, you get a bent shape. So that is, again, that sort of methane shape. Like that's a bent shape there. And imagine that was an oxygen. That would be exactly the shape of the water molecule. 2 bonding pairs and then 2 holes there where the lone pair electrons would be. Okay, that's enough wittering from me. So that takes us to the end of the lecture. Quick reminder, valence shell electron pair repulsion theory is dealing with the valence shell of an orbital, which is the of an element, which is the outermost shell of that element. The electron pairs is to do with the orbitals in there, and repulsion is them moving as far as possible from each other as they can. Remember that we're looking for groups of an electron, and I'm defining groups as electrons responsible for joining an atom to another, or lone pairs in there. And the minimum size of a group is 2 electrons. You can never have groups of 1 electron, or rather, in this course, we won't. Brilliant, and there's a summary of the shapes there. In the bottom, I'm representing the lone pairs with a slightly different colour of atom at the top. And that's the end of that lecture. Thank you very much.